in the last subsection, I promised the last string matching algorithm in this unit. I want to talk about another one, the Rabin Karp algorithm, which also has its pros and cons. And one of the big advantages of this algorithm is its space usage. First of all, well, we've already seen, just as a recap, a worst case optimal algorithm, and we've seen one that has slightly better typical performance, whatever that means, but maybe for English language text, it's better. What else could we hope for? And one thing they all do is, apart from storing the text and the pattern, they at least need extra space as much as the pattern is long. If you have really large patterns, that is maybe not desirable. And at least in theory, you can ask, is this necessary? Do we need extra space to do pattern matching? Remember that brute force does not need any extra space apart from these two variables, I and j. So you can definitely do pattern matching or string matching. So string matching and pattern matching is the same. Some people prefer one over the other. I think string matching is slightly more telling. So I'll try to stick with that. You can do string matching without extra space apart from these two variables, but then it needs n times m time. Can we somehow get the best of both worlds? And Rabin Karp is essentially yes answer to that. And it uses a lovely idea that doesn't pop up otherwise in this module, which is a shame in itself, so I want to at least teaser this. That's the idea of hashing. The idea is very simple conceptually. You have this pattern string. You can compute a hash of the pattern. Think of it as a fingerprint that is smaller than the pattern. And then for each guess in the text, you can compute this fingerprint. And if the fingerprints are different, there's definitely no match. If the fingerprints are the same, the way the fingerprints work in this case is there could be false positives. With a hash, you have collisions, so it can happen that two things have the same hash, the same fingerprint, but they are not the same. Fingerprints for humans, I guess, tend to be fairly unique. So if it's different people, they have different fingerprints and vice versa. For hashes, this is not quite the case. You can have the same hash and still be different. So if we find that the hashes agree of the pattern and the portion of the text, then we have to still check all the characters if it's a real match or just a spurious false positive. But hopefully we don't have these often. For the examples in this section, I'll use numbers. So you can think of the alphabet as being the digits, just because then the hash computations become more natural to write down. But the same works for other alphabets. Just the math uses different numbers, but you remember it's all binary at the end of the day. So here's a text, a long sequence of digits, and here's a pattern. Can we somehow find where it occurs? And with the idea of hashing, we need a hash function. So we need a way to reduce a pattern of a certain size to a single number that we can quickly compare. And one not completely stupid way to do this is to take the number modulo a prime. And so here we just have x modulo 97 as an example. If you take this for this pattern, well, take my word for it that the remainder, if you divide by 97, is 95. I don't think there's an easy way to check this other than doing the math. And now you can try to find this in here in the following way. The first guess would be these 5 digits. If you compute the hash of those, it's 84, so definitely not a match. If you shift this by 1, look at the second 5 characters, compute the hash, it's not 95, so it can't be the match. And you keep going like this until at this position you compute 95, and in this case indeed it is the pattern, so yeah, there is an occurrence starting here. And we could find this by just comparing the hashes. A first attempt to write this into code, which will work fine, but is slow for a reason I'll show you in a second, is this. So first we need our hash function, and we'll stick with the idea of using essentially the number modulo a prime. So we pick some prime number without getting into the details how to do this. It's not relevant for our discussion. Well, I feel I can't leave this as this. What you want is a number that's not too big so that the result fits in one word, but you don't want it too small, otherwise you get many collisions. So you probably want to pick a prime number that's just below 2 to the w. And it's efficient to find these, and they can be pre-computed for once and for all. Then we can compute the hash of the pattern and store that in HP. And then for each guess, we compute the hash of the text at this position. If the hashes agree, we might have a match. We still have to compare. So we do a character-wise comparison. I just abbreviated this here by saying we compare the strings, but really this is m individual character comparisons. And if they match, we return the position. Otherwise, we keep going. Now, this is fine. It's correct, the algorithm as given, because it always checks if we have a collision of if they have the same hash, then it checks, and if there's a different hash, it definitely is not a match. The problem is that the computation of the hash itself takes linear time in the length of the pattern, because the hash function depends on all the positions, and so there's essentially no better way than computing this one step at a time, walking through the string. And we do this for each guess in the array here. So we have n minus m, roughly n times m. So that's the same worst case as for brute force. And indeed here it's not even worst case. We do this every time. We have to compute the hashes of all the guesses. So that's not great. Fortunately, we can do this slightly faster, slightly smarter, by exploiting the exact form of the hash function that we used here. And the idea is that we always go from one position in the text to the position one later. So it's not like we need the hash of two completely unrelated positions in the text. Almost all the characters stay the same. It's just a little inconvenient that they're shifted around. There's the first character deleted and a new one added at the end. But with a little trick, you can actually update the hash for this specific hash function in constant time for that kind of operation. And the trick is you pre-compute, for our pattern length, you pre-compute this number, which is just the number of digits, 10 to the number of positions in the pattern. The old hash, say, for this number is known. And now we would like the next hash. And I mean, I just point out again, these are all the same. We deleted the 4 and we added the 6 at the back. So how can you compute this using what we already know? The new hash is the old number where we subtract the first digit. So we just have to shift the first digit by as many zeros to the left as needed. Then we get 1592. We multiply that by 10. That shifts a 1 to the left. And then we add the 6. Okay. And one convenient property of modular arithmetic is you can take the modulus first and then do the arithmetic. They commute, as you may remember. And so we know the result of this one, modulo 97, that's 9. That's what we pre-computed. And we know this one, modulo 97. So that's the previous hash, right? So we can reduce these big numbers where the computation would be slow to the small numbers that fit in one word and are computable in constant time. And the rest is just a little bit of arithmetic, but it all involves small numbers. They're independent of the size of the pattern. That's the important bit. That's why we pre-compute this number and just use the hash here instead of the full pattern, the full number. Okay? I spelled this out in code, but there's no surprises. It's doing exactly what I explained. In the general case, you want to pick a radix that's not necessarily 10, but some number that's at least as big as the alphabet. You can use it slightly bigger. And why would you sometimes want to use a bigger radix? It's convenient to have a power of 2, then the multiplications become shifts. And so it's even slightly faster, even though it doesn't affect the theoretical runtime. The modulus should be some large prime, but so that things fit still into one word. And you can show that all the numbers are never bigger than this. And here, that's the computation I explained on the last slide, just neatly written up in one formula. The rest of the code is unchanged, right? We go through all the guesses. If the hash is match, then we check all the occurrences. And before we go to the next match, we update the hash so that it is the hash of the next position. How good is this? The expected running time is as good as we can hope for in the worst case, m plus n again. There is a worst case in if you're very, very unlucky and your hash function produces lots of false positives, you always have to check all the characters. Now, if our prime number is deterministically fixed, if you pick this once and for all, then some nasty person could work through your hash function and produce a text and a pattern that always gives you false positives. But if you pick this slightly randomly, so you have a certain range for the prime numbers and you pick a random one, you can turn this worst case into something that is astronomically unlikely. We had the same discussion for quicksort, where you can pick a random pivot and enforce that the average case becomes the usual case and is not dependent on the input anymore. We achieved what we wanted initially. We only need constant space. If you check the algorithms, the only thing that is stored is a few extra numbers and the hash of the current position and the pattern. And these all fit into one word, so it's a constant amount of extra space in total. And another cool thing about this is it extends to other situations. It's not just for strings. You can use this for finding certain 2D patterns in pixel images and things like that, just because this fingerprinting idea is very versatile. And same, the hash function can also be updated if you shift a segment of a matrix around. Let's do one more of these. Same kind of principle, just reiterating what's good and what's bad about the algorithm, and be precise about what the guarantees are. We get a few more. I have only one more slide to show after this question, so I can give you a sec. All right. Seems most everyone's done. 3, 2, 1. Locked. There you go. Seems pretty clear. So let me just briefly do this. So if we drop the check, right, if we don't do this extra check, we only rely on the hashes, then we might report positions that are not real matches. We will never overlook matches, so maybe this is still useful. And then if we do this, if we omit the check, then the worst case running time is n plus m. So that's why maybe this is useful depending on what you want to do with it. Sometimes it's fine if you report all the correct matches and some extra ones, and you can later deal with them. It's just something to point out. So you might run Rabin Karp without the check if you don't need it to be always correct. Then it's always fast, but sometimes gives additional results. If you want it to be always correct, then it's sometimes slow. And that brings me to this last slide that just summarizes the algorithms we've seen for string matching in terms of different categories. How much time they need for pre-processing, how much time they need during the searching phase, and how much extra space they use. The last column we haven't seen yet, but we will see. And it's probably fair to say that there's no algorithm that completely dominates all the others. It depends a little bit on the circumstances which one is good. Boyer-Moore tends to be well used in practice because it strikes a good balance. And Rabin Karp is liked for its extendability to other settings.